What's up, guys? Welcome back to the 12 ISLs of Christmas. In the past 4 videos, we were discussing problems in the shortlist 1 position, such as A1, C1, G1, and N1. And over the next 4 days, we're going to be stepping things up a difficulty by looking at some harder problems. And we start by looking at 2017 IMO shortlist problem N3, which is shown on screen here. And it states to determine all integers n greater than or equal to 2 having the following property. For any integers a1, a2, all the way to an, whose sum is not divisible by n, there exists an index 1 is less than or equal to I is less than or equal to n, such that none of these numbers are divisible by n. And here we let ai equals ai minus n, when I is greater than n. So let's understand what the problem statement is saying. So we know that there's a index I such that all of these numbers are not divisible by n. So we get ai plus 1, and so on and so forth. And we go up to all the way to ai plus n minus 1. And when we have this, we have to go back down, because that means that this is ai minus 1. So at some point, we're going to hit ai plus all the way to plus an. And then when we hit this, we go back to plus an plus a1. And then we continue from here. The point is that we're going to kind of circular in the sense. So it may help to look at the numbers on a circle. In general, when we have these type of prefix sums, a good idea is to put the numbers on a circle, because then we're summing the numbers on the arcs. So let me go ahead and draw this circle. We have A1, A2, A3, A4, A5, and then so on and so forth, all the way to AN minus 2, AN minus 1, and AN. Then what the problem statement states is that for some point here, suppose A3, there exists some point on the circle such that whenever we consider the sum this, and this, and this, and so on and so forth, all the way to this, then none of these numbers is divisible by n. So what if the problem statement was false? Then what would happen? Well, then for every single one of these points on the circle, there exists some index that makes the sum equal to 0 mod n. In other words, it's divisible by n. So from a1, we could go all the way to suppose a5 and get that it is 0 mod n. And from a2, we could go all the way to a3 only, and a3, we could just pick a3 itself if we wanted to, and a4 could go all the way to a6. You get the idea. So how do we use this idea? Well, now we have to use a condition in the problem that we haven't used yet, because we can't just continue going around in circular arcs like this. And the only part of the problem that we haven't used is that the sum is not divisible by n. So how can we use this? Well, if we want a sum to be divisible by n, then we want to somehow go from all the way to here and go around in a complete circle ending at an. So because if we end at an, then we cover all these numbers the same number of times, and therefore k times the sum a1 plus all the way to plus an is divisible by n. And we want to get something good out of this. So how do we get the arcs to add up to the complete circle? Well, suppose we have a1 through a4, as I said earlier here. Well, since this doesn't add up to the complete circle, we can just keep going, because we end up getting a5 to suppose an minus 2. Then we just continue going from there. We get an minus 1 plus suppose a2, and then we continue a3 all the way to suppose an minus 3, and then finally we get an minus 2 all the way to an. And this completes the circle. And notice that each number is covered two times total, as shown here. And that means that the sum is 2a1 plus all the way to plus an, which we know is equivalent to 0 mod n, because each of these arcs are divisible by n, the sum of the numbers on each arc. So that means that the sum of all of the numbers on all of the arcs is also divisible by n, and just this number here. So if we can do this, then it would be great. But the question is, how do we get to this position? In other words, if we continue from A1 and continue going circular, how do we know we'll get back where we started? Well, consider the starting positions of each arc. Because we have A5 all the way to AN minus 2, so we can just list the starting positions. We have A1, A5, AN minus 1, and then we continue down. And if we have n plus 1 of these arcs, then we must repeat ourselves eventually. Like we must get back to, suppose, A5. And this is true by the pigeonhole principle. If we have n plus 1 objects going into n bins, then 2 of those objects must be in the same bin. In this case, the bins are the AI, and the objects are each of these arcs. So that means that 2 of these arcs must start at the same position. So we have like A5, AN minus 1, A7, suppose. We go all the way to A5. And when we get to A5, the number on the last arc must end in A4. So that means that this section here completes the entire circle. So how many times does each point appear in our sum? Well, if each point appears n times in our sum, then we get na1 plus all the way to plus an is equivalent to 0 mod n. And that's what summing all of the arcs gives. But this is clearly true because we just multiply by n, and anything times n is divisible by n. So this tells us nothing. So the only way we can not have problems is if all of these numbers are covered at most n minus 1 times. So how do we prove that each point is on at most n minus 1 arcs total? Well, notice that we have a bunch of these numbers here, and they're at most n plus 1 numbers here. So that means that from what we said earlier, we only use n of them. We only use n arcs total. And each arc is at most n minus 1 numbers in length. So that means that the total length of all the arcs is less than or equal to n times n minus 1. And since we use n numbers on the circle, that means that each number is covered at most n minus 1 times, and we're good. All right, so now we know that k times a1 plus all the way to plus an is equivalent to 0 mod n for some 1 is less than or equal to k is less than or equal to n minus 1. So when does this imply that a1 plus all the way to plus an is divisible by n? Because when this is true, that means that we've run into a contradiction. Well, if n is composite, then if we write this as ab, then this could be a and this could be b, and that's bad. However, if n is prime, then that means that each of these guys one of these guys must be divisible by n. And clearly k is not divisible by n, which means that this sum here must be divisible by n. And that's bad by the problem condition. So therefore, the problem holds true when n is prime. And now we just need to deal with the composite number case. In the case of composite numbers, it definitely seems like the problem could be false, because as I said earlier, writing it as AB, we could write it as A and B. Alright, so now we've shown that prime n work, and all that remains is to tackle the composite number n case, which you probably know doesn't work because our argument seems to break. So let's write n equals AB as we did before, where A and B are greater than or equal to 2. Then we want to somehow use this fact and get a sum divisible by n by writing, suppose, ABs or BAs. So if we write ABs, then we can go B, B, all the way to B, then zeros all the way through. And suppose there are A of these. Then this works because then we can just go through the entire list and get back here. However, then the sum is divisible by AB, which is n. So what happens if we just add an extra b here so that there are a plus 1 of them? Then if we started this b, then we can just go here. If we started this b, we can just go here. And if we started a b here, then we go here, then we continue going past, and then we end up here. And such logic holds for all of the b's on the list. And if we're at 0, well, the sum is already just 0 mod n, so we don't need to do any work there. So therefore, this construction works. And to prove that the sum is not divisible by n, this is clear, because the sum is just ab plus b, which is equivalent to b. And since b is greater than or equal to 2, but less than n, we know that it's not equivalent to 0 mod n. To see where this argument would break when n is prime, we note that if n is prime, then this would be 1, 1, 1, 1, 1, and this would be n plus 1. But then there would be n plus 1 numbers in a list that has n numbers, which is bad. So that's where the argument when n is prime breaks. And when n is composite, this argument works just fine. So therefore, composite numbers don't work, while prime numbers do. And we are done. So what's the takeaway from this problem? Well, the first one, as I discussed earlier, is to draw the numbers out on the circle when we have this type of periodicity and when we have these type of prefix sums. Because drawing them on a circle can allow you to visualize things pretty easily. And second is, by looking at it on a circle, we were able to visualize the argument clearly. Meaning that we could just continue going around the circle until we hit a fixed point, or get back to where we started. And we proved that we could get back to where we started by using the pigeonhole principle. And when we get back to where we started, that's where we finally use the part of the problem that we didn't consider yet, namely this part here, where the sum is not divisible by n. So thank you so much for watching this video, and I'll see you guys tomorrow for the next